Hello, Math 135 students. I am here with a video of some extra examples from section homework module 5A and 5B this week. So we're looking at, in this unit, we're looking at, first of all, how many ways can we count or arrange things into different groupings, different ways to do things. That's kind of the first homework. And then second homework then turns that into the probability questions. So when you are doing like a counting problem, you're going to notice a lot of times it says the words how many. How many ways are there to do something? So let's look at this first one. It says how many four-letter code words can be formed from the letters A, B, C, D, E, F, and G if we have the following stipulations. So first of all, a four-letter code word means that there are four different spots that we're going to be filling in. I like to think of them as blanks if I'm just individually filling in each spot with the number of choices. This is related to the multiplication principle. So it says if no letter is repeated, well, first of all, we have 7 letters. So the very first slot, there's no really restriction here. You could pick from any of the 7 choices. But as soon as you place one of the letters here, we don't know which one it's going to be, but once it's placed, it's out of the game for the next choice because no letter can be repeated. So we would then have 6 choices and then 5 and then 4. So it's up to us then to just multiply the number of choices for each letter to be filled all together. And that comes out to 840 ways for the first one. Now, the second one is a little different, and I'm going to try to minimize the writing utensil to a thinner line. It says if the letters can be repeated. So again, 4 spots. And this time we still have 7 choices for the first one because you can use any of the 7. And since you can repeat letters, you have all 7 choices for each individual letter code spot. So this is 7 to the 4th. And if we do that on our calculator, that comes out to 2,401 ways. Notice there are more ways when you can have repetition. And then the last one, it says, and this is a phrasing they use in the homework. They use successive, I noticed in one of the homework problems, but it's also in the textbook. They a lot of times will use the word adjacent. So I put both phrasings here just so you could see that they mean the same thing. So adjacent or successive letters must be different. Okay, so let's think about what that means. That means whatever we place in the first spot, we can't place that same choice in the next spot. So that's the restriction here. It doesn't mean that number or excuse me, that letter couldn't show up further down the line. They're not saying it can't be repeated anywhere. They're saying it can't be repeated next to itself. So we have 7 choices for the first letter. And whatever we pick, let's say we pick A. Well, you can't put A here. So now you're down to 6 choices. Okay. Now for the next spot, say this was B. Again, we're just speculating here. Well, I can't put B here, but I could put A again. So A is kind of back in play. So this is again 6 and the same situation here. You can't put the one that was going to actually fill the spot, but you can put anything else that's there. So 6. So it's 7 times 6 times 6 times 6. So the restriction isn't that you can't repeat letters. It's that you can't have the same letter next to itself. Okay, so let's work this one out. So this is 7 times 6 to the 3rd, which is 1,512 ways. Okay, so there's the number 1. All right, so a lot of what you do, in fact, in this first section is they talk a lot about Venn diagrams in the notes and the kind of the videos and in the textbook. Venn diagrams are a way to visualize different set relationships. When we talk about a set, we're talking about kind of a list of objects or items or numbers. And for us, a lot of times it's going to be numbers and they have characteristics. So, you know, maybe the set of, maybe A in a problem is a set of all even numbers between 0 and 10. So, you know, you have parameters and things like that usually set up when they're dealing with the numbers. This one is given to us in terms of music students. So it says a class of 30 music students. So that's our total universe. It's important to know when you're talking about set theory, the universe is all of the items that are going to be in our Venn diagram. Our Venn diagram has to add up to that 30. It includes 13 people who play piano. So I'm going to let one set be P for piano. We have 16 people who play guitar. so that's going to be G. And then we have 5 people who play both. Now we learned in the notes that that is an intersection when you do an and. So that's the intersection of P and G. So I like to draw the Venn diagram before answering the questions. Sometimes you can do them in your head, but especially when you get like 3 sets, it gets a little more complicated. So we have P, we have G. The entire box represents the universe. Sometimes they'll write that in here, and that I think that's a little misleading. I mean, it's not if you know what it means, but sometimes people will think that's just the outer part here, but this entire rectangle and the circles contained inside of it is our universe. And then we know that we have our intersection is this portion in the middle here. It's where the 2 circles P and G overlap. Now, when you're filling in a Venn diagram from given information, usually we're going to work from the inside out. So we're going to start with those people who played both, and we're going to place those here. That's 5. Now, the thing you have to remember is that even though this says 13 played piano, it's anybody in the P circle. So actually those 5 people count as part of this 13. So we only put what makes this add up to 13 in the P not G. That's kind of how we talk about this. This is P not G. So that would be 8. And then for the guitar, not both piano and guitar, that part is, let's see, 16 minus 5. So that's going to be 11. So now we have what, 13 and 11. So I try to add all that up on the side over here. That's 24. And we're supposed to have 30 students in the class in all. So there's 6. So that means there's 6 people in the class who don't play either piano or guitar. So that answers our first question. How many students in class play neither of those instruments? Well, now we know from our Venn diagram up here, there are 6 students that fall into that situation. How many students in the class play piano only? So that's, again, this is part of that right here. I like to kind of highlight sometimes. Let me see if I can make that smaller. So this is the group piano only, because they don't also know how to play guitar. So that one right there is going to be the 8 students. Let's see if there's a part C. No. Okay. So let's look at number 3. It says a couple is planning to have 3 children. How many boy-girl combinations are possible? Distinguish between the combined outcomes such as boy, boy, girl, boy, girl, boy, girl, boy, boy. What they're saying with that is they're saying birthing order is going to matter. They're considering having 2 boys and a girl different depending on where the girl was born in the birthing order. So that's what they're telling us to do, to distinguish between different orders of first child, second child, third child. So let's start a tree diagram. So the first thing you have in a tree diagram is the first choice. So we're going to have that first child has a choice of either being a boy or a girl. I don't know that they technically have that choice when they're in the womb, but you know, that's the choices we are presented with. They're either going to have a boy or a girl. So first child. From there, we branch out to the choice for the second child, and we're going to have to do this for both the first branch down up at the top and the second branch at the bottom. So it's either going to be another boy or a girl from the first boy, so boy, boy, or boy, girl. And then we have the girl could then be followed by a boy, or the girl could be followed by another girl. And then for third child, again, because there's 2 choices each time, we could have boy, girl, boy, girl, boy, girl, boy, girl. So if we wanted to write out the list of our set, if we wanted to actually list out all of our possible sets, we could have boy, boy, boy. I'm just following the tree branches, boy, boy, girl. Now I've exhausted all branches off of that route. We could have boy, girl, boy. We could have boy, girl, girl. We could have girl, boy, boy. We could have girl, boy, girl. We could have girl, girl, boy. And then girl, girl, girl. And sometimes the tree diagrams are really useful if you're doing some probability problems down the road because it helps you get this set listed out. Because there's actually a way to, because we can count this up. There's 1, 2, 3, 4, 5, 6, 7, 8 different ways for that someone to have 3 children and to figure out the different outcomes of the boy-girl possibilities. So we could quickly get that by just of using the multiplication, I can't talk, the multiplication principle. If you think about each child being a choice slot, a choice that we have to fill, and there's 2 genders to choose from each option time, that's 2 to the third, which is 8. So it's quicker to do it this way, but when you're doing probability or, counting ways, sometimes later on down the road when we're doing the probability, we might say, what's the probability of having 2 girls out of 3 children? Well, then nicely here, when you've got the sets listed out, I could see that there's 1, 2, 3 different possibilities out of the 8 that give me that option. So it is sometimes nice to have a tree diagram just for the creation of the set list instead of just knowing how many ways. Okay, so in how many ways can 4 people sit in a row of 6? So we're looking at, okay, for these next a couple ones that we have, we're getting into the section 7.4 on the difference between permutations and combinations. Permutations, the order matters, and in combinations, the order does not matter. You're usually picking a subset from a larger number of things. So if we look at this first one, it says is how many ways can 4 people sit in a row of 6? So rows are ordered arrangements, like a lineup essentially. So we want to know where can we put these 4 people, and the order is going to matter because we're sitting them in the row. So that's going to be a permutation. We have 6 chairs essentially, or places that we can put people in a lineup. And we're going to be placing or permutating or picking, I like to say it picking sometimes, 4 people for those different arrangements. So you have this button on your calculator. I do know that that's there, but there's also a formula. This is NPR, and that is n factorial over n minus r factorial. So that's our permutation formula. So when we look at this, this is 6 factorial over 6 minus 4 factorial. So that's 6 factorial over 2 factorial. And remember, a factorial is the multiplication from that number all the way down to 1. Now, obviously, I could have stopped here and just wrote that as 2 factorial because that's what I have in the bottom, but kind of seeing the expansion sometimes helps. So we're doing 6 times 5 times 4 times 3. So 6 times 5 times 4 times 3 is 360 ways. Okay, let's look at the next one. It says how many 4-person committees are possible from a group of 9 people if there are no restrictions? First of all, it doesn't seem like it matters. When you make committees, unless you're giving someone a position of power or, like the first person picked is the president, then usually a committee is just grouping something together as a set and you don't really care what order they were picked in. So this is going to be combinations. And if there's no restrictions, that means we can have 9 people choose 4 of them for the committee. Now, again, we have to know our formula, but again, it's on your calculator. It's NCR is n factorial over n minus r factorial. And then we also have r factorial. Now, again, certain books may use different letter choices for these, but it's essentially the same formula. It's always the number of items factorial divided by the difference factorial, and then the repeating. The r factorial there is standing for all of those different ways when you do a permutation that you have, like, say, the same 4 people, but they were in a different order. So when we work this out, this is 9 factorial divided by 9 minus 4 factorial divided by 4 factorial. So I'm going to write these a little bit more compactly. That's 5 factorial and a 4 factorial. Usually I take this one down to the bigger one in the bottom and then I stop. So 9 times 8 times 7 times 6 times 5 factorial. I put the factorial back on there because this is still 5, 4, 3, 2, 1, but that allows me to cancel it with the 5 factorial in the bottom. And then I'm going to expand the 4 factorial. So 4 times 3 times 2 times 1. The reason for doing that is you can now reduce some things. Like 4 times 2 actually makes 8, so we can reduce that. And 3 reduces 6 to a 2. So it's 9 times 7 times 2. So 9 times 7 times 2 is 126 different ways that they could form that 4-person committee from a group of 9 if there are no restrictions. Now, if both Jim and Mary must be on the committee, that means that we really aren't choosing all 4 people anymore. So when you have something like this, sometimes people will write it, just depends on your instructor. Like we know we have to have Jim, we know we have to have Mary, and we need 2 others. Randomly, don't care who the other 2 are. Well, Jim is 1 person out of the group and we're choosing him, so 1, choose 1. Mary is 1, choose 1, because we're picking them. We can't pick anybody else. They specifically have to be on there. We now have only 7 members of the group that are not in the committee yet, and we need to choose 2. Now, a lot of times people won't write the Jim and Mary part. They just know that if Jim and Mary are fixed, that's like multiplying times 1. Essentially, there's only one way to pick Jim and only one way to pick Mary. So we're just really doing the 7 choose 2, because 1 choose 1, by the way, is 1. So let's work out the 7 choose 2. That's going to be 7 factorial over 7 minus 2 factorial and 2 factorial. So 7 factorial over 5 factorial times 2 factorial. 7 times 6 times 5 factorial over 5 factorial. So that's going to cancel. And then I'm going to expand the 2 to 2 times 1. And that 2 can go into the 6 and make it a 3. So this is 7 times 3. This is only 21 ways. A lot less. If Jim and Mary both have to be on the committee, you're really only picking for those other 2 slots. So there's 21 ways that can happen. Now, either Jim or Mary, but not both, must be on the committee. This is a little different. So this is saying that one of the slots will be Jim or Mary, but there are 3 other slots or positions on the committee that can be filled by someone other than them. It can't be one of them. They have to still be thrown out of the group for that, because then you'd have both again. So essentially for this, Jim or Mary have to go into slot 1. And then we're going to have how many ways to choose the other 3. Okay. So Jim or Mary, there's 2 people in that group. If you consider them like their own little subset, we're going to choose one of them. Times, because we're still, when you're doing a selection where you're making multiple item selections back to back, that is the multiplication principle. So you are saying it's this for the first slot, and then this for the second slot, and then this for the third, and this for the fourth. So you're multiplying until you complete your entire set. So 3 others. Now you can't use Jim or Mary, because no matter which one I picked, if I put one of them back into the play for the other spot, they're going to have both of them on the committee. So we want to make sure we can use 7, but this time we're choosing 3 members to fill out the rest of the team. So you should notice that this is the whole group of 9 and this is 4. So we still have 9 total members and we are still choosing 4. The way it's done, we're splitting it up into the scenario of the restrictions they've given us. So anytime you have a number choose 1, that answer is always going to be just that number. You can work out the formula, but it is 2 choose 1 is 2. So I need to work out 7 choose 3. So that is, and I'm going to do that over here to the side. So 7 factorial over 7 minus 3 factorial. And again, you can use your calculator. I'm just showing my work. That is 4 factorial times 3 factorial on the bottom. So 7 times 6 times 5 times 4 factorial over 4 factorial, which can cancel. Expand 3 times 2 times 1, and 3 times 2 is 6, so that cancels that. So it's 7 times 5, which is 35 over 1. So this ends up being 2 times 35, which is 70 ways. Okay. So let's see what we have next. All right, we have an electronics store receives a shipment of 30 graphing calculators, including 6 that are defective. So I like to, when I see these are kind of quality check problems, and they show up a lot in the probability section as well. The first thing I like to do is go over here and write that I have 30 total graphing calculators, and they're split into essentially 2 subgroups, even though they only told me about the 6. We have 6 we know that are defective. That means in the group of 30, 24 of them are good. Okay. Now, they're going to be sending 4 calculators to the local high school in that area. How many selections can be made? Notice the first one, no restrictions at all. We don't care if they get good ones or bad ones in this first scenario. So that uses the whole total 30 that we had. And we're choosing 4. Now, again, we don't care what order calculators are picked in. It's not like picking the first calculator means that it goes to a very specific student or anything like that. There's not an order to that. So 30, choose 4. So 30 factorial over 30 minus 4 factorial and times 4 factorial. And again, you can use your calculator. I'm going through the steps just so you can see more and more familiarity with how the formula is actually working when you use it on your calculator. So 30 times 29 times 28 times 27 times 26 factorial. So that can cancel. And then we expand the other one, which is 4 times 3 times 2 times 1. And I'm going to use a different color to distinguish the cancellations here. So 4 goes into 28 7 times. 3 can go into 30 10 times. And we can also reduce 2 goes into 10 5 times. So I am doing 5 times 29 times 7 times 27. 27,405. And again, I know your calculator can get that really quick. I just like showing students what the calculator is actually computing and doing. Now, how many of these selections, because this is just if they just blindly kind of grabbed 4 calculators, not caring if they were good or bad, and just took them. There's 27,405 ways that could happen. How many of those selections would have been a grouping that had no defective calculators? Well, to do no defective, that means we want to know specifically, did I choose all 4 from the good pile? So this would be 24, choose 4. And if you want, you could also write 6, choose 0. That always ends up being 1 when you do a choose 0. If you work the formula out, you can see that. So if you're thinking about breaking up from the group, I am still having 30 items, but I only chose 4, and I chose all 4 from the good. Now, a lot of times people, when they don't choose something from a group, they won't write the 6, choose 0, and that's okay. You can just write 24, choose 4. We know that that means we are specifically focusing on that one subgroup. So let's work that out. So 24 factorial over 24 minus 4 factorial times 4 factorial. So that's 24 times 23 times 22, because this is 20, by the way, I didn't write that down, times 21 times 20 factorial over 20 factorial, and then I'll expand the second one. So this is the 20 factorial cancels. Let's use a different color for the reducing step. So this is 4 times 3 is 12 times 2 is actually 24. Sometimes if you multiply all this together, it actually matches one of the numbers on the top, because this is 12 times 2, which is 24. So they actually completely cancel that out. But you could do that in smaller steps as well. So 23 times 22 times 21 is 10,626. So if we multiply that by the 1, because I did write my step there where I chose nothing from the defective group, this would be 10,626 ways. Okay, and then I believe this is my last one from section 5A, and then I'll have my second video I'm going to record right away and have that for you. Oh, nope, there's 2. Okay, so we have 7 and 8. So this says a jewelry store chain with 8 stores in Georgia, 12 in Florida, and 10 in Alabama are planning to close 10 of these stores. How many ways can this be done? Well, it's important to know total jewelry stores, because if we're going to do no restrictions at all, just how many can they close, we need to know how many jewelry stores we have in all. So 8 and 12 is 20 plus 10 is 30. So there are then 30 stores, and those are broken down into 3 different states. So if we don't care which states they close them in for this first question, they had no restriction, that would just be 30 choose 10. And again, closing them in a specific order should not matter. I'm going to go ahead and set up part B as well, and then I'm going to get a calculator and work these out since you guys have seen me do quite a few of the expansions. So the company decides to close 2 stores in Georgia, 5 in Florida, and 3 in Alabama. Okay, now that's very specific. So we're going to be closing from specific subsets. And we still have to multiply all of our combinations together because we're still closing a total set of 10 stores. So from Georgia, that would be 8, choose 2 stores, times 5 from Florida, so 12, choose 5, times 10 in Alabama, choose 3. Okay, so we want to work all of that out. So let me pause this for a second and grab my calculator, and I'll work these out on that. Okay, so 30 choose 10 is going to be 300, 4, 5, 0, 1, 5. So let's see. So 30,045,015 different ways. Now, they have the more specific. Let's look at these individual closings in each state, which is usually how things are done. It's done regionally more than just globally like that. So 8 choose 2 is 28. So I'm just going to write down my answers for each part. 12 choose 5 is 792. And 10 choose 3 is 120. So if we multiply those together, that is 120 times 792 times 28. That's 2,661,120 different ways. So lots of different possibilities there. All right, so let's look at the very last one for section 5A. So it says a nominating convention will select a president and a vice president from among 4 candidates. Campaign buttons listing a president and a vice president will be designed for each possible outcome before the convention. How many different kinds of buttons should be designed? Now this is going to matter because if you're choosing a president and a vice president and those are roles that are being assigned, that's permutations. That is an ordered selection, because having Biden-Harris is different than Harris-Biden on the pin, because you see the person listed as the president and the second person as the vice president. So we're going to be doing 4 total candidates. Pick 2. So this is going to tell us the number of ways that the 4 candidates can be ordered arrangements of 2, and that will tell us how many different buttons we need. So we have to do our permutation formula, which is 4 factorial over 4 minus 2 factorial. So that's 4 factorial over 2 factorial. This one's not too bad. 4 times 3 times 2 factorial. This is just 12. Okay. All right, that is the end for the 5A video.